I'm Rebecca Ann Heineman. I've been in the video game industry for the beginning of time. Many of you look like old enough to have been there at the time when we were using sticks for ones and rocks for zeros. But my career started off as a video game champion, which then led to people actually recognizing that I actually had skills of 6502-based computers that were all the rage at the time, namely like the VIC-20, the Commodore 64, the Atari 400, 800 series, the Commodore PET. One of the reasons I got myself an Apple II was because the Commodore 64 didn't exist yet, and somebody was selling one on a, it was called the Penny Saver. It was one of those little ads you open up, and it has, basically called Craigslist today. But someone was selling an Apple II for some reason for $600. And I'm like, what happened? Did this fall off the truck or something? But it ended up that his company ordered a bunch, and he was just tasked with getting rid of them at whatever price that he sold them for, or he can get for it. So $600 later, I had an Apple II, which was essentially the sum total of my life savings at the time. But I managed to drag this thing home and started programming on it. The fun thing about the Apple II was that when it was created, it was designed from a circuit board that was supposed to be nothing more than a text terminal, the Apple I. Many of you have heard the Apple, but if you actually use an Apple I, you will find it really is nothing more than a glorified teletype. I mean, it had a text mode, but you couldn't even couldn't even write to the text mode. You actually had to write to a port. And a chip was used to generate text much like a teletype. Now it sounds, I can hear it better. But that basic idea and concept was then used to create a brand new computer, the Apple II, which had, of course, video graphics, text, and other modes such as that. Other computers were designed by people who were sane and didn't both look like a hippie and probably smoked some serious drugs, because the hardware from the software perspective really was something that whoever designed this was on some seriously good drugs. Because on the Commodore 64, video is arranged pretty much linearly. You start your video graphics page at 0, and you sequentially go through memory, and that is how, and just go sequentially, and that gets you to your text screen. Your video buffer, when you're doing graphics, is a little bit weird because you could see they were just using the text mode for fonts, because the graphics was 8 bytes solid vertically, then the next 8 bytes, the next 8 bytes. So if you were drawing a horizontal line, you just skipped every 8th byte to draw a line. So you get a base, draw a line, and every 8 lines you do the new base. The Atari 800 used a thing called the Antic, and can't remember the exact name of the system, but essentially it's a scan line display buffer, in which you just tell it, okay, I'm going to describe my screen saying, go to this memory address, draw some 160 pixels of graphics, go to the very next line. So when you create your screen buffer, it's again linear screen. And of course, both Commodore and Atari, when they did their bits for how you describe the graphics, 2 bits per pixel, great. Grab a byte. There's 4 groups of 2 bits. There's your color. Same. Now let's go to the Apple II. God. Yes, you start at the left of the screen, 0, you draw 40 bytes. There's 40 bytes of graphics. And then if you go linearly, you go about, think of like 40 lines down, and then that's the next scan line when it comes to linear memory. I'm like, wait a minute. I don't just add 40 to get the next scan line. I have to go all the way down in memory to something like about 400 bytes hex ahead. And that's why whenever you see a video game on the Apple II that just fills the memory to blank the screen, it has this Venetian blind look. It's because the scan lines are not linear. They are interlaced, something like, I think of like 8 groups. It's either 8 groups or 4. I think it was 8, but it's one of those things where, after 40 years, my memory is kind of a little. But, okay, we can draw graphics on the Apple II by just simply drawing 40 lines of, let's say, FF to get some white, 0 to get some black, and using what we call a Y table, in which you just take the Y coordinate of your graphics you want. You go to this table of 16-bit values, which will tell you what the scan line actually is, use as your base address, and then you could draw that line. Okay, problem solved. Now let's go to that 2 bits per pixel. This is where a lot of Apple II programmers would realize, you know what, I should have stayed on the Atari. Instead of being 2 bits per pixel with 8 bits of graphics, no. It's 7 bits. What you do is that you have to do your graphics in 2 byte pairs. The first byte has 3 2 bits per pixel, fine. But then there's 1 bit left over, which is carried over to the very next byte. And then that is the remainder of the 2 bytes per pixel. And then you have 3 more 2 bits per pixel. So in other words, 2 bytes gets you 7 color pixels, not 8. Which is one reason why the resolution on the Apple II, instead of being 160 color pixels across, is 40. But what is that extra little bit there? What is it? Is it there because someone was insane? Magic 8 ball? Probably. Okay, got that. But waste not, want not. Steve Wozniak, the inventor of the Apple II, decided that why don't we just use that little bit to determine the color clock, and if that's clear, you leave the color clock alone. If you set it, you offset the color clock by half a clock. So in other words, instead of using 4 colors, which usually is black, orange, and blue, or it would be black, white, green, and like a purple, or I think it was. So you could essentially choose 6 different colors because black is always black and white is always white. So those 2 colors, you toss them in the garbage. But if you draw with, let's say, colors of blue, you now have to pattern them because every single byte is either 1 or 2 palettes, except for that odd man out who's straddling the 2 palettes. And you have to deal with the fact that, okay, you have half a green pixel here, but now it's a half a purple pixel over there. Especially when you have a character, let's say, I don't know, I'll just use something more contemporary, Mario, and you have him drawn in this orange color because, red didn't quite exist on the Apple, and having him run around, but as he's running around, he sometimes shifts in color because he's near something that's in the other palette and you're drawing the 2 on top, which is one reason why in the Apple II there's a lot of little artifacting going on. So we have nonlinear graphics, we have 7 bits per pixel, and the fact is that if you run this on a black and white display, you're going to find out exactly how the colors were shifted. Because on black and white, there is no chroma whatsoever. What's going on is just taking the bits and just displaying them as is. But then you will, on images that have the high bit set, their bits are literally moved a half a bit. So therefore, when you draw graphics on the Apple II and some places where it's supposed to be color, you'll see that they don't quite line up with the pixels. It's because it literally is a high resolution 280 pixels that's actually doing half shift, so it kind of pretends to be 560 pixels. So heaven help you if you want to draw, let's say, black and white text on a color monitor. This is the reason why you get all that color artifacting, because the hardware has no idea whether or not you're trying to draw text that's actually in color or in black and white. So when games are designed, like the original Apple II games like Space Invaders and Pong and Asteroids, which are all done for black and white monitors, you play them on a color monitor and all the images have this color artifacting. So these are all the things you have to deal with when drawing graphics on. So that's one reason why when you see games that I'm doing, or I've done back in the past, the fonts usually have very thick lines. It's only because I want to do 2 bits per pixel as much as I can to get past the color artifacting. And I have graphics that are usually set in specific spots, like Bard's Tale, so that therefore when they are drawn, I don't have to worry about the images being moved left or right. But for games like like Mind Shadow and Tracer Sanction, which I actually have animations running in which they can move anywhere they're on. I do have to make certain, like let's say there's a shark fin and it moves around in Mind Shadow. And what I did is I made certain the background was all blue. So therefore, when it draws, it doesn't have to do the color artifacting. Well, this is we just got past graphics. You think the drugs stopped there? Oh, hell no. Let's go to sound. On the Atari, they have this chip called the Antic and the TIA. And I don't remember which chip it is specifically, but it had a beautiful sound synthesizer. You know, with you just set what waveform you want, you set what frequency you want, and after you set the registers, the sound's going, and then you can just go on and do other pieces of code. And then, secondly, the Atari 800 has interrupts. So you can actually write an interrupt driver that runs 60 times a second, so it can play the music and sound effects without the main game code even happening, and with minimal use of the CPU time. Commodore, they obviously followed Atari's lead, and they came out with the SID chip, which was, again, beautiful sound. You just go ahead and set what waveforms you want. And the Apple II, you have a single I/O register, C030. What do you do with it? You access it, and then it causes a speaker to move in. You access it again. It causes the speaker to move out. I have just explained the sum total of Apple II sound. And literally, that is Apple II sound. Now, of course, they redeemed themselves many years later with the Apple II GS, but I'm going to stick with the Apple II right now only because I want to make all of you go psychotic. So, with the Apple II, Steve Wozniak, for whatever reason, decided not to add a 555 timer or some sort of countdown chip and an interrupt. So therefore, not only do I have to tick the speaker and tick it again and do so for every single iteration of a beep I want to make, I do not even have an interrupt driver, so therefore I cannot do music per se because the main code has to stop, loop to make a tone, but then as soon as it goes back to the main code, sound stops. Because nobody's there sitting there like a, what is it called, a railroad handcart, you know, trying to get the sound to keep going. This is where games like Borrowed Time, Tass Times and Borrowed Time and so forth, the music in there was basically just a couple of tones, and then the game progresses, and occasionally when there is a sound effect, you will notice that the game stops momentarily. Because on the Apple II, you literally have to say, to make a sound effect, I say, this is the loop, this is how, you know, I tick the speaker, I sit in a little idle loop for X amount of time, then I tick the speaker again, and based on that amount of time I do between ticks will determine what tone I play. And then, of course, if you have, let's say, a sound effect like static or like that, you actually have to have your code change the delay it is between the ticks. So anybody who does anything more than beep is going to have to do a lot of gymnastics in order to be able to play sound on the Apple II. Well, this is where I read a lot of white papers and stuff, because on Bard's Tale 3, I did not want the music in the game to be nothing more than beeps and bops that every time it happened, it would cause the monster animations to freeze for a little bit. So, learning what MFM and frequency modulations and so forth, I was able to get two sounds out of the Apple II, in which I created a carrier wave that was about 30 kilohertz, and then on that, I would have two different tones in which I would then be changing the, I would do the frequency, but every now and then I would pause for a little bit and then reverse the frequency. And I would do that based on two tones simultaneously, in which when you listened to Bard's Tale 3, you actually heard chords. And you're like, wait a minute, this music is not one sound, it's actually two. And that's because when you take two frequencies and you add them together, you get this third frequency, apply it to a carrier wave, and it's called FM radio. So effectively, using an FM frequency, which is in this case 30 kilohertz, because that's the fastest I can go on a 1 megahertz Apple II, you're able to do two tones. One of these days, I'm going to be getting around to uploading the source code to Bart's Tale 3 to GitHub or something like that, and you can then see how the sound was done. Now, just to let you know, I wasn't the first one to do it. There was actually something called Music Tracker that was done like 2 or 3 years beforehand, and they did the same technique. I just listened to it, go like, okay, challenge accepted. But this doesn't still solve the problem of interrupts, because you see, this is all based on hardware timing, and accepting the fact that the Apple II you ran at exactly 1 megahertz. So therefore, if you ran with an accelerator or with a Apple II GS or later on the 4 megahertz Apple IIc, the sounds would be 4 times higher in frequency. In those particular cases, that's where you have to, if you want to hear the sound the way it was meant to be heard, you have to turn the accelerator off before playing the game. Now, let's go on to the development environment. This is where the Apple II actually doesn't suck. And this is the main reason why I was attracted to the Apple II in the first place, other than the fact that one fell off a truck into my pocket for $600, was slots. Unlike the Atari and the Commodore, which were designed to be all-in-one computers, the Apple II was intended for you to lift the lid off and plug some cards in there. And of course, the circuitry to plug the cards in was simplicity itself. On the Apple II, the way the memory map works is from memory location 0 to BFFF was just RAM. C1000 to CFFF is the hardware memory locations. D1000 up is ROM. Can be switched for RAM, but that's another story. In the Apple II, location C1000 through C0FF is the hardware register. Actually, no, C0 through C07F is the hardware registers. This is what controls the Apple II and all its behavior, etc. But then you have C080 through C08F, C090, C09F. These are 8 groups of 16 registers that don't exist. They actually exist on the peripheral cards, and there's an actual select line, one individual to each one of the peripheral cards. So therefore, if you put a card in slot 1, and it just looks for that one line, then anytime memory location C090 through C09F is accessed, all the card has to do is say, oh, this line got pulled, check the lower 4 bits of the address line, and put up whatever register that I feel like putting up there to implement my card. Then we do it again for memory location C100 through C7FF, in which C1 is slot 1, C2 slot 2, C3 slot 3, etc. There's another line, gets pulled down, and it just says, hey, you got a 256-byte ROM? Enable it, put the lower 8 bits on the bus to figure which byte you want. There's your ROM. And then, finally, at C0800 through CFFF is shared ROM memory, in which there, all cards can put a 2K ROM in there, but if you access memory location CFFF, you're supposed to relinquish control. So hit your card, C090, it tells the card, oh, I have control. Now if I go to C800, there's 2K ROM for whatever the card is, if the card supports it. Why are you even bothering with this? Because when I got my Apple II, I liked Atari 2600 games. But unfortunately for me, I couldn't afford Atari 2600 games because I spent all my money to this guy who basically gave me a computer from the back of a truck. So I, like any other enterprising individual, would go onto the bulletin boards, or in my case, the actual Apple II manual that came with my Apple II, which had the schematic for what was called the Apple II integer card. This card was just a ROM card that plugged into one of the slots of the Apple II. Well, all it takes is saying, if I just add a read-write line to the ROMs, I could put in RAM chips in there. If I put in a 74LS245, I could make a buffer, and then if I have a flip-flop, I can make two buffers. One goes to the Apple II, and the other one goes to this funny little cable, which goes over to a little combat cartridge that I remove the ROM from and put in this cable. And then at that point, using another cable, I could plug it into a cartridge into it and read it, all based on the schematic of the Apple II integer card. This allowed me to copy Atari 2600 cartridges. So once I downloaded these cartridges and put them into RAM, I would then be able to put them on this modified integer card. It actually is a card I wire wrapped from parts at Radio Shack, may they rest in peace. The place where, like Fry's Electronics, may they rest in peace, where they would have wire wrap tools and sockets and chips. Man, those are the days. But was able to build my own little Apple II card, all wire wrapped. It's now sitting in the Video Game History Museum in Frisco, Texas, if you ever want to see it. But with this, I was able to download all the cartridges, put them up on the Atari cartridges, this fake combat cartridge, and I was able to basically copy every single cartridge there was. But I wasn't going to stop there. You see, the Apple II, those of you who know will know what call -151 is. That is the command that when you turn your Apple II and your Apple II Basic, it will take you into what's called the monitor. It is a command prompt that is connected to a little tiny BIOS who has a disassembler. This is where it gets some coding here. The disassembler allows you to just simply look at memory in the Apple II, either through a memory dump, or disassembles the opcodes into actual 6502 code. Funny thing about Atari cartridges, they're legible because they were also written in 6502. So by looking at the 6502 code, looking at using the Apple II disassembler, I was able to learn how to program the Atari 2600. But then I thought, you know what, why don't I actually start making games in the Apple II? So when you're making games on the Apple II, now to explain to you the wonders that is the video graphics system, the wonders of the audio system, and the fact that every other platform out there was far, far superior, yet I was seeing games out there like Serpentine and Space Invaders and so forth on the Apple II, and they were all going like, I could do that. So there was this game that I saw back in 1979, I think it was called Mission Asteroid from Sierra. Now, Mission Asteroid is just basically one of the first graphic text adventures. The text adventures are not new. I mean, Zork predates it, and then Scott Adams' Adventures predates that. But I saw that this game was using just draw commands and in order to draw the art, so you can have dozens of pictures on a floppy disk, which, 140K aside, come on, winner. So you can take a 2K, was it 2K? Let's see, it was from 4K to, so it's about, it's about too much, but it was 8K. You have a video picture, which is about 8K memory, but you need to be able to compress it. Well, all the compression algorithms, the best ones even out there, will only get half the space. But if you just simply store the draw commands, you can only have maybe anywhere from 100 bytes to 500 bytes to just describe a picture. So, how to do this? How to duplicate that? Well, I just went ahead and created my own little graphics programming language, which would just say, a byte would say draw command 0, followed by the X coordinate of where to start the line, the X and Y coordinate where to end the line, and then I would have another command saying pen color, so that would just say, okay, draw in black or draw in white. Then there would be another command for drawing a circle, which would then give me the origin and radius. But to do this required some interesting techniques in programming the Apple II. The Apple II only runs at 1 megahertz. The 6502 takes a minimum of 2 clocks per instruction. So even no-op increment X, so forth. They all take 2 clocks. So effectively, your maximum throughput is 500,000 instructions per second. So how do you improve upon these speeds? On the Apple II, many of the instructions would be such as like load A, but a 16-bit address, comma Y. And that's hard-coded, and the address, of course, is hard-coded in the instruction. Then there would be instructions like load A with a 0-page location, which would have the pointer, and then you index it by Y. The problem with that instruction is it takes 6 clocks. 2 clocks for the instruction itself, another clock for the actual byte that for the 0-page address, 2 more clocks to go to 0-page to get the address, and then another clock to read or write the memory. And of course, if that happens to cross a page boundary, it's an extra clock that's just thrown in for fun. So this one instruction could take 6 clocks in order to read or write a byte of memory somewhere in space if you want to go ahead and have this one little piece of really brilliant code that would read memory from a graphic, write it to the screen, and repeat and fill. Well, there's a problem with this. And the main issue is the fact that this really slows down your ability to draw. Now, back then, computers had nothing like multitasking, multi-threading, so then therefore, there is no reason why anyone would have to worry about what's called self-modifying code. So many of my routines, what they would do is that when I generate the address of where I was going to draw my art, instead of actually storing it in a direct page or 0-page location and then using one generic piece of code to do the draw, instead, I would actually modify the instructions ahead so that they would then say, okay, instead of being load A at 4,000 hex, comma Y, it now becomes load A with 5,000 hex, comma Y. And same goes for the destination. I would change that one too, because that instruction, load A 4000X, takes 3 clocks to read the instruction, the instruction itself, the 2 bytes for the address, and then the fourth axis is the read or write itself. So instead of going from a maximum of 6 clocks, I knocked it down to 4 clocks. But there are ways of doing this even better. There's techniques I use in the 2GS, which I actually fold the graphics page to the stack. And I just use push effective address or push A and write memory in there. But those are only available on the 65816. On the 6502, self-modifying code was one of the things. But then there was another technique which I used on some pieces of code or pieces of the game in which I had a lot of space. And this is what was called compiled sprites. As you can imagine, when you're wanting to draw a sprite on the screen, you have in memory the actual bits of the sprite, and then just reads from the sprite and writes it to the screen. Well, what if you could say the sprite is aligned with bytes on the screen, so you never have to shift, and you also know that the sprite is never, ever going to clip any of the screen boundaries? Now, if you could guarantee that, like I was able to do in some animations in Tass Times and Tonetown and in Tracer Sanction, what you do now is you actually generate a piece of code. In this case, I use a small script in BASIC to create it, and then I use the assembler to assemble it. But what the code does is load A with the first byte of the shape, 2 clocks. Instead of load A, go through a pointer, index by Y, go here. No, it's load A with that. Then, let's just say the shape is like a rectangle with some little X's, or corners cut off. Well, what happens if maybe about 20 bytes of the shape is the same value? It's all FF. So now the code would say load A with FF, store, all indexed by Y, with each store being offset as to where it would be on the screen based on the Y coordinate. And then I would load A with the next version of the shape, or in some cases, let's say the next byte is 7F, I would actually generate an instruction, arithmetic shift left, which turns the FF into 7F with one instruction, 1 byte, still 2 clocks. And then do store again. This technique I use for both fonts, and I used it also for some specialized graphics in which I knew that the Venetian blind effect wouldn't come into play, but it would allow me to draw these shapes at unheard of speeds, and allowed me to focus on draw the art as fast as possible, then play a little bit of sound, draw some more art as fast as possible, play a little sound, so that now when you're playing Bard's Tale 3, you would be wondering, how in the world am I drawing this art and still playing sound at the same time? The technique of using compiled shapes was how I did the fonts on Bard's Tale 3. So therefore, and what's funny is in some cases, the code was actually smaller than the font itself because of the fact that I had the ability to read one value and just write, and not have to read another value at all. So it cut the speed of the draw in about half. Other techniques that I used, let's see here, the good ones. Oh yes, the disk drive. Let's go there. On the Apple II, the beauty of the disk drive is that it is directly tied to the hardware and the bus. The drive itself is completely software controlled, in which stepping the head, reading from the shift register, and so forth, those are all software control, which allowed people to create some very, very creative copy protection schemes on the Apple II. C64 and the Atari 800 were actually way ahead of their time, because today we all use USB drives and no one thinks anything of it. But back then, their disk drives actually had CPUs, RAM, ROM, everything in it, and you communicated with them serially. So therefore, it's one of the reasons why Commodore 64 and Atari 800 disks tend to be a lot slower than Apple II. And secondly, the options for copy protection are extremely limited, which is one reason why a game like Mule, one of the most top-rated Atari 800 games ever, for floppy, only sold a few thousand copies because of the just rampant piracy. But on the Apple II, remember I told you 140K on the side of a floppy? We can do better. The way it happens is that on the Apple II floppy drive, the way it's supposed to be is when you write out an entire track on the disk, you're supposed to first turn on the write head, first let the head settle, get to the appropriate place, turn on the write head, and then you write D5AA96 and some information to determine to say, this is sector 0, an epilogue, then you wait a little bit, and then you write a D5EEAD, and then you write the actual data, and then you're done. Because of the fact that these are done by precise timings, that is, you have to read if you want to modify just one sector, you have to wait for the sector previously to move by. As soon as you can read the sector, read the epilogue, knowing that the head's going by, you have to wait a few microseconds, and then after that, turn on the write head, write out the sector data, and because of drive variance speeds, you have to have some wiggle room between sectors. Well, what if we could use that wiggle room? Some of you have heard of a technique called 18-track sector, or 18-sector tracks. This is a technique in which what you do is that you just clear off the track, first turn on the write head, clear the entire track, and then you write a single group of source bytes saying, hey, this is D5AA96, or whatever numbers you want, and then you follow it with 18 sectors worth of data consecutively, no breaks. So then once the entire track comes in, because there's enough space in there for 18 tracks, 18 256 byte sectors, if you do not have any space between adjacent sectors in order to handle the ability to arbitrarily read and write sectors on the fly. And of course, when you're shipping a game, the game is hardwired, hard-coded, so you're never supposed to be modifying the sectors. So what the heck? So what will happen then is that you go ahead and create the epilogue, and then you just write 18, and therefore you will also know that when you make the head revolve around just once, you read the entire track, which, when you're running at 300 RPMs, you can read an entire track's worth of data in 1/300th of a second, which on the Apple II, due to the way interleaving works, you really technically have to have 4 revolutions to read an entire track. Because the way it works is that it's sector 0, then sector 4, then sector 8, then sector 12, then it goes to sector 1, so forth, and that's how the sectors are actually mapped on the disk, because that way you would read in sector 0, then you take some CPU time to munch on it and digest it, and then by the time you're done and you want to read the next sector, the floppy already puts the sector 1 should be coming up, but it's still going to take 4 revolutions to get the entire data. Well, when I presented this idea to Activision for Mind Shadow to do the single sector track, their first reaction was, that's a great copy protection. Too bad none of our vendors can actually duplicate that. So I contacted the vendors and wrote the software for them to modify their drives and stuff like that so they can actually write and duplicate these types of sectors and so forth. Now, for Mind Shadow and Tracer Sanction, we actually never did use that particular scheme, but I had a side business where I was going to duplication houses and selling them different copy protections. So I'd say about maybe a quarter to maybe a third of copy protection disks probably have my fingerprints on it, whether or not I actually had any direct involvement, because it was a turnkey system. Basically, is you give them your unprotected disk, you apply my software to it, they then use their disk duplicators, and that's the reason why a lot of copy protection schemes look the same, because it literally is mass-produced. But, undeterred, how in the world can I still read an entire track in 1 revolution, but have to deal with the fact that the tracks are formatted the right way? That's where I came up with a technique where I wrote my own read-write track sector. Now, on the Apple II, RWTS, read-write track sector, is a piece of code whose job it is to go move the head to the certain track, read in the sector, give you the data, but of course, the post-processing was what took the time, which is what limited you to reading a track in 4 revolutions. Well, I looked at the algorithm, and I saw that the algorithm was taking what they called, again, I may be off on some of these specifics, but it was GCR encoding, in which I believe it was 4 bits to 3, or is it 5 bits to 4? It takes this 8 bits of GCR data. The first bit is garbage because it's just a clock bit, but then the other 7 bits, you then apply it to a table, which will then tell you exactly what the real bytes are, and you store it into a buffer. What the original Apple II read-write track sector did was it read in about 300 and some odd bytes into a buffer, then it ran this algorithm on the buffer to turn it into 256 real bytes, and then gave it to you. Well, by using 3 different lookup tables interleaved with the code that read in the actual hardware registers of the disk drive, and using self-modifying code, because instead of the Apple II's code, which would be saying load A with a memory address and then it would take 6 clocks to read, mine was load A with C068C, comma X, and C0, and of course I would be modifying that 8C to be exactly what slot it was in. So in some cases it was just load A with C08C, C0, it was all those registers were direct, so I didn't even have the index by X register, which is necessary because I needed that X register, because as soon as I would read it, it would be load X with the value that I read from the floppy drive. Index it into this table, pull up the value, get the next value from the disk drive. Well, of course, 32 cycles apart, because there's some very, very strict timing. It's 32 cycles between each byte being read from the floppy disk. I would then read in the next byte, get the next thing. Once I think it was patterns of 4. After I read in 4, was it 3 or 4? I don't remember exactly specific, but I would read in the 3 or 4 bytes, use the lookup tables, and it would actually generate me 2 real values, and I would store it directly in the resulting table. So as a result, by the time I had finished just reading the 300 and some odd bytes from the floppy disk, I already had the decoded data. There was no pass where I had to go in and read in the data, then go in and use an algorithm to convert it into the real bytes. It was done all at once. So therefore, what I would do is I'd move the head to a track. Then whatever sector came by, let's say sector 4. Okay, sector 4 comes in. I would then set the destination pointer to where the 4th entry of where I was going to put to. I would then read in that sector, decode it immediately. Then whatever the next sector was, oh, it's sector 8. I'll put it in location 2800. Read in the sector, go to the next one, 2C100. And of course, because it was arbitrary, as soon as I had 16 sectors read, I just counted. As soon as a sector came in, I counted. Okay, as soon as all 16 sectors were counted, I would then verify, did I actually read one of every sector, which the answer was yes. Because if the answer was no, I had a read error and had to do it again. But with this, when you played Mind Shadow, when you booted it up, it booted the entire game in 3 seconds. Because it literally was, the delay was how long it took for the head to move from track to track. Because I would just boot the game, 256 bytes from the boot block, which would have a piece of my little code, reads in my read-write track sector, which is another 8 blocks. After that was done, then the code would just say, okay, move to this track, read the entire track. Just move the track, and after every revolution, so since I was doing it once every 300ths of a second, and it took about a quarter to a half revolution to move the head from one track to the other, I was able to read in about 40K of data in approximately 3 or 4 seconds. It was like when the game boots, you could see the graphics. And this was the technique I used because it was a way to optimize how to read in the data, convert it from GCR to actual bytes, and do it at the speed of the drive as the data was coming in. Later on, I used this very similar technique when I did a game called Borrowed Time for the Commodore 64, because in that case, I uploaded code into the Commodore 64's disk drive, which, by the way, is also 6502, if fancy that. And I actually had the same types of buffers in there, which I would read the track in one revolution, and then I would have a high-speed serial communication, not the Commodore's communication. I had my own, which then loaded the data into the Commodore 64 memory as quickly as possible. With this, it was allowed me to create, my game Borrowed Time, Tass Times, and Tonetown, which the loader was going very, very fast. And people loved it. In fact, people were thinking like, wait a minute, is this a cartridge game or is it a floppy game? No, it's definitely floppy. But these are all the techniques that were used there in order to speed up the disk drive. Fun fact, when I told you I was doing hardware tinkering, I didn't stop there. In order to test the 1541 modified card code, I made a card on the Apple II with a 6522 VIA, which basically is a duplicate of what was in the Commodore 64, and I plugged my 1541 too. And I was using my Apple II to actually write the code, upload it to the 5041, debug it, test it, and so forth. So by the time it was actually running on the Commodore 64 it ran the first time because all the code was developed, hundreds of iterations were all done on an Apple II. That card also is sitting in the the Video Game History Museum. But of course, I didn't stop there. Those of you who are curious, if you have a copy of Tass Times and Tonetown for the Commodore 64, go into it with a sector editor. If you do so, you will find that there is a catalog on track 13, which is the directory where the Apple II stores its directories. Because, actually, no, take it back, it's the other way around. The Apple II ProDOS stores its directories on track 0. The Commodore puts its directories on track 13. So on track 13, I had a fake Commodore 64 directory and everything. So if you put it into a drive and you type in directory, it'll say TAS and system.prodos and stuff like that. But if you actually went to track 0, there's a ProDOS directory because I actually wrote an Apple II driver that used that serial card to be able to read and write sectors as a ProDOS disk. So therefore, on my Apple II, when I developed a version of Tass Times and Tonetown. It was drive that just mounted on my computer, and I just simply copied the files with just file copy, except it was using the 1541's communication protocol to read and write the sectors. But it was an actual ProDOS disk, ProDOS file system, ProDOS everything, and I wrote a little mini ProDOS in which what it does is that when Commodore 64, we put the disk in for TAS, it says ProDOS system, or TAS.system, it's actually ProDOS. You put it in there, and it goes through the ProDOS boot system, and it boots that floppy as if it was an Apple II. And it ran the game. And the game thought it was running on an Apple II, except, of course, with a completely different video driver. But the final question here is like, why the hell did I do this? Why in the hell did I go through all this trouble to use the Apple II as my host machine? I wasn't the only person out there making peripherals for the Apple II. Titan Technologies created the 3.6 megahertz Apple II accelerator, which on it had 64 of memory. This board was like packed with chips on it. But I put this thing in my Apple II, and I was running at 3.6 megahertz, which meant compiling code on Merlin was a breeze. Then, of course, came the Axlon RAM disk. This is something, of course, I still have one left, but of course its battery's long dead. But what it is, it's a RAM disk. On it, it had 320K of glorious memory, a battery-backed up RAM, and a controller that read the memory into my system as fast as possible with a special driver that made it appear to me as a floppy disk. Because that's how I was working it with DOS 3.3 before I moved to ProDOS. Because most of my original development was under DOS 3.3 on the Apple II. With this development environment, an Axlon RAM disk, a 3.6 megahertz CPU, it took me only seconds to do a build of any of my games. So I would write the code all in assembly, get everything, hit build. It would then use the RAM disk for reading and writing files, which means what the hell is a track delay? What the hell is a propagation? Whatever, it just was instant. And then once the code was built, then I would use either the serial drive or I'd just be running on the Apple II, and I would test the code. With this rapid iteration was one of the reasons why I was able to write so many games in such a short amount of time. Because if you look at my career, I've got my name on about 250 titles. And when you divide this out to my career, it's like, wait a minute, that's like one every 6 weeks. And, well, I was churning out a game or port every 3 weeks. And it was because this Apple II with an Axlon RAM disk in one slot, a Titan 3.6 megahertz accelerator in another slot, and either a Commodore 64 disk drive controller that I built or an Atari 2600 ROM emulator, which I also used for ROM emulation on the Commodore 64 in another slot. It gave me the equivalent of what you all call the PC Master Race deck that people these days are bragging about, saying, ooh, I got a Threadripper, or I've got all these wonderful bells and whistles. Well, technically, that's what I had, except this was the year 1980. I only have like 10 minutes left, so if there's anybody who has any questions, I can go ahead and do it before I go ahead into another Burger Time rant. All right, what can I waste another 9 minutes left? Oh, wait. Oh, yes, you.
The best burger you've ever eaten.
Red Robin Bonsai Burger.
Do you still get it?
Yeah, Red Robin.
Okay. Yeah, well, I didn't know cycle flavors.
No, you can still, no, that one's a burger. Now, I will share you with another secret. Go to Red Robin, order it to go, take it home, find a nice desk drawer, put it inside, keep it in the plastic paper bag because it absorbs any moisture, leave it in there. 72 hours, precisely. After 72 hours, peak of flavor. Yeah, very fermented. And then, of course, to add it better, just before you decide, around the 73rd hour, run down to McDonald's, get an order of fries. Come back, fries, burger. Bon appetit. It also allows me to be as immune to pretty much every virus and disease known to man because I think every single virus and disease is already partied down in my body. So take for what you will.
You got it from the desk.
Huh?
If not from the burger, you got it from the desk, maybe.
Yeah, I mean, that desk has seen things. If it could talk, it'd probably just scream nonstop. And yes, you.
How did you get the idea for Tass Times?
Friends of mine who took shrooms. That's an interesting story. Tass Times in Tonetown was created by Mike and Muffy Berlin. Now, you may, at least the story, I created the game engine and everything, and I worked with them extensively saying, no, you can do that. Yes, you can do that. No, you can do this. So I was just as much of a creator, which is technically is my game. But essentially, my best tagline to it is it's the closest thing to a drug trip without actually taking drugs. But the whole point of the game was just basically, I wanted a game with a story that was so off the wall, so crazy, so stupid, that people will just be flocking to it solely because it's not another, oh, the princess is in the castle, go through the quest. I mean, yeah, King's Quest has made a lot of copies of it, but, it gets old after a while. And, of course, with Tass Times and Tonetown, people would look at the box and go like, Tass Times and Tonetown, what the heck is that? And, of course, it got people to pull the box off the shelf and look at it. And, of course, the thing that really helped Tass Times and Tonetown was when I was developing it, Apple was 1985. Apple was creating this brand new machine codenamed Cortland, which, so as you would know, is the Apple IIgs. And since they already knew I was an insane Apple II programmer who was making games like crazy, Apple was able to give me one of the prototypes, to which I ran Cortling with a friend of mine, Russell Lieblich, may he rest in peace, to create that opening soundtrack, which is when you play the 2GS version, it goes do-do-do-do-do. Now, we had that same song on the Commodore 64 and the Apple II, but, when somebody said, here's an actual synthesizer chip, do you think I was not going to go ahead and molest it? And as a result, it became one of the top-selling games on the Apple IIgs ever, because when the Apple IIgs finally did hit the store shelves, it was running Tass Times in Tonetown, and it was running the music soundtrack, and people were going like, a computer can make music like this? It put the Amiga to shame. And remember, in 1986, people were all talking about trackers and stuff on the Amiga and saying how the Amiga is far, far better than the Apple II will ever be. And now this thing called the 2GS shows up and kicks the Amiga's ass. And subsequently, when I did Bard's Tale 1 and 2 for the Apple IIgs, you can hear the polyphonic soundtracks and so forth. I mean, it literally was taken from what I learned from the programming in Sonic MT32. No, ESQ1. It was the ESQ1. It's the Roland was the MT32. But I actually learned how the ESQ1 worked with the people over in Sonic, they're telling me all the dark secrets, which I, of course, applied to programming the Apple IIgs version of Tass Times in Tonetown. But yeah, interrupts are great. Please, why didn't he put interrupts in 1970? I could have done so much. Anybody else? Because I'm about ready to be kicked off this stage. Any last minute questions? Oh, yes, we have a question over here. Volunteer?
So for the, let's see, for the GCR decoding,
yes,
the high-speed stuff, did you end up, is that sort of one loop per byte, or did you have to unroll it since it's, I think it's 6.2 is the...
It might have been 6.2. Again, it's one of those things where the specifics are something that I haven't even thought about for 20 years, so the little details there. But what it is that there was like 3 or 4 different states of the byte, because it's basically there was 3 bytes or 4 bytes. I don't remember specifically, but each one is a different grouping of GCR to actual bytes, and it was literally 6 bytes it decoded into, or 6 bits it decoded into. So I think it was 4 to 3. But what happens is that I would have 4 tables. So I would read in the nibble that came in, looked it up in the table, and the table would give me the actual 6 bits that are decoded, pre-shifted to where it's supposed to go. And I would read in the values, and of course with some extra clocks, because I don't need 32 clocks just to read in and do a lookup table, but I would then do some pre-shifting. I would then get the other bytes shifted out. So like if it's already pre-shifted, I would just read the byte and store it in a temp or just keep it in a register. The other one I would read in the next nibble or in with a different table, but it was all designed so that it would take no more than read in at 32 clocks. It would take 128 clocks, but in that 128 clocks precisely, I would read in the 4 bytes, output the 3 true bytes, and then we do this all over again. And it's what allowed me to read a track in 1 revolution. I do have the code to that game, and it is my intention, I'm going to be just letting everybody here in the Federation know, that I am planning over the next couple of months going through my Apple II collection and posting it up on GitHub for everyone to see. And since I have 2 minutes, I just have time for one more question before I'm given the hook. Who wants to be my volunteer? Well, I already gave you my burger recipe, so there you go. All right. Well, thank you very much for having me over, and I hope to see you again next year. Thank you. And of course, follow me on Twitter, Burger Becky. Follow me on Discord, Burger Becky. I have a YouTube channel called Burger Time, where I do basically these rants whenever I feel like it. And again, Burger Becky, so just follow it on every one of the social medias. So thank you.